let's start with some review, okay? We're going to finish the chapter today, and the last thing we were talking about last class was the topic of salt solutions, okay? And whether those salt solutions were acidic, neutral, or basic. So first and foremost, what do I mean by the word salt? An ionic compound. You're right, okay? And what I'm going to do is I'm going to bring up an example, and we're going to go through, once again, to review with you, the thought process of how do you decide if a salt is going to give you a pH below 7, at 7, above 7, okay? So this is the example that we're going to start with today. Ammonium chloride. And just because it is a habit for me, you don't have to do this. Okay, I like to draw a line to separate the cation and the anion. Okay? Now what do ionic compounds do when you put them in a water environment? Most salts will ionize. They split apart. So our major species list is going to include the ammonium ion, chloride ion, and of course we always have water. And the thought process is, with salts, is you look at each ion individually and you try to decide, will that ion react with water, yes or no? Okay? So let's go through the thought process. The cation, okay, of your salt, cations form possible bases. Now, I want to say something about this particular example. If you look at some of the salts we looked at last class, the cations in those salts were metals, like lithium, sodium, okay? And when I said to you, okay, cations form a base, what base might this cation form? All you did last class was you took that metal and you attached OH to it. So you said things like LiOH, NaOH. If your cation is not a metal, like that is not, that's a polyatomic ion that contains hydrogen. If your cation is not a metal, it's a polyatomic ion that contains hydrogen, in order to predict what is that base that this might form, this cation is going to act as an acid. It's going to give away one hydrogen. So you tell me, guys, if this cation gives away one hydrogen, what base is that we've seen before? What base is that? NH3, which goes by the name of ammonia. Strong or weak? Oh, people. Weak, thank you. Let's review that, shall we? What are your strong bases? Cabacer
Group 1 hydroxide.
and group 1 hydroxides. Ladies and gentlemen, ammonia, NH3, doesn't even have hydroxide in its formula. There should have been no for strong. Okay. Okay. The anions are easier to deal with. The anion of your salt forms a possible acid. To predict what acid that is, all you have to do is attach H to that anion. What acid is that could form? Hydrochloric? Strong or weak? Strong, okay. Now, I know I've asked you this a zillion times. What does it mean if an acid is strong? What does that mean? Completely ionizes, complete dissociation. Does HCl, this strong acid, does that sound like a compound that would prefer to be together or apart? Apart. Strong things don't form. This anion, ladies and gentlemen, is not going to react. And what do you call an ion that doesn't react? It just hangs out in the beaker. It's a spectator ion. Okay. What does it mean to be weak? Does not dissociate much. So that base that we said this would turn into is something that, yes, will form. So as weird as this sounds to say it, it's the weak side. Whatever you have the W above, that is the side of the salt that will react. Think of W as standing for will react. Okay. Let's think about what that equation, that reaction is going to look like. Ammonium plus water. And what was the base you said again that it would form? Ammonia, okay. And what would my other product be? Hydronium, very good. Okay. No numbers. Okay. Yes, we're going to form ammonia, but look at the other product. Ladies and gentlemen, if you're causing a reaction to occur that produces hydronium atoms, or molecules, excuse me, where do you think the pH is going to end up? Below 7. When you are producing H3O+, you're going to end up in the acidic range. If you look back last class, the problem that we did last class, what was in this position right here wasn't H3O+, it was OH-, which is why our pHs last class were above 7 in the basic range. Okay? Now, if I were asking you not just to predict, is this acidic, neutral, or basic, if I was asking you to calculate a pH, you'd have to do an ice table. And let's see what you remember from last class. At the bottom of that ice table, you'd have x squared over some number minus x. What kind of K would you want for this particular reaction? Ka. Do you remember how you know that for sure? Right here. Ask yourself the question. If what I'm adding to water, what is this thing? What is it doing left to right? Is ammonium, you guys tell me, is ammonium donating a hydrogen or accepting one? Donating. It's an acid. So I need a Ka, which I might give you. Or, because I love to torture you, maybe I won't. Maybe I will give you this. Maybe I give you that. Can you get that Ka that you need?
Yes.
Where are you going to look? Where are you looking? The formula sheet, you have an equation that looks like this. Ka times Kb equals Kw. Do you remember what this equals? It's written right above. 1 times 10 to the negative 14th. You can always find whatever it is you need. Okay. Let's look at a practice problem. I'll get it started for you and you're going to finish it. And I chose this particular salt for a reason. Here we go. Ready? It says, calculate the pH of a 0.25 molar solution of blah, 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 blah. That's its technical name, by the way. Okay? It says the Kb for pyridine is blah, blah. Okay. That is a salt, ladies and gentlemen. Is that a compound that you are familiar with? No. Ha, me neither. Okay. I get in the habit, because that's just helpful for me, of drawing a line where the cation ends and the anion begins. Yikes. What do you think? Okay, some say between N and H. Some say this. Let's fight about it. No, I'm kidding. Okay, here's how you're going to figure this out. Are you ready? And I'm going to say something. I'm going to say it twice because I want to make sure that you hear it. Okay. If you are being asked to calculate, not just predict, is this acidic, neutral, or basic, but actually calculate something about a salt. Your salt must either be one of these combinations. It's either a strong-weak combination or a weak-strong combination. You will not be calculating anything for strong. Do you remember what that is? pH of 7. Okay. And weak, we'll talk about how you deal with that, but you won't be calculating anything. So some part of that salt should create something strong. And we are intimately familiar with our strong acids and bases. Oh, of course. Of course. How could you doubt us, Miss G? Shame on you. Okay. So, does that change your answer at all? Anybody want to make a more definitive guess? Drum roll. Here we go. Da 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 da! That's where it splits.
Wait, what? No.
Oh, yes.
No, that's wrong.
Okay, look, listen.
That's wrong.
Okay, remember, let's go through the thought process again. Your cation, listen, cations form bases. Does this look anything familiar to you? Really? Okay, the answer is no for most of us. If it's something that doesn't look familiar to you, what letter must we write above it? W for weak. Because we know our strong things. Okay? Now, come back to what I said a moment ago. If you're being asked to actually calculate something, one part of your salt must have an S for strong above it, which is this side. Now listen carefully. This is how I knew where to put that line. Are you ready? Anions turn into acids. Please notice I did not say anions are themselves acids, because they're not. Cations become bases. Anions become acids. Now can you see why the line is there?
Yes.
Okay. So I'm going to help you with this next part, which I personally think is the hardest part, which is writing the reaction. Okay? Now, which side of the salt is the side that's going to react? The weak side. Yeah. Okay. Fine. So I'm going to write all of this. Now, hold on a second. Cation. That implies it has a charge. It's positive, right? Cations are positive. Positive what? How'd you know that? For sure. Oh, so good. You guys know your polyatomics? Of course you do. Perchlorate has a -1 charge. Of course, see, you knew that. I know. I'm asking a lot here, I know. Okay. If you're feeling a little nervous, like, yeesh, this is something I'm not familiar with, I'm not really sure what the products would be, let me say something to you again. If your cation is a metal, all you have to do to predict that base is just slap an OH on it. Well, this isn't a metal. All you have to do to create that base is treat this as an acid, which it is. And what do acids do, people? They give away their hydrogen. How about we just take this one off? That seems pretty convenient. So how should I write this base that I'm going to form over here? Does this have a charge? Neutral, negative, what? It's neutral, okay? And my other product will be? Hydronium. You guys are so smart. You're welcome. Okay. To me, that's the hardest part. Do you think you can do an ice table from here and solve for pH? You can. All right. Go get them, tigers. Or cougars, whatever. Wrong big cat. All right. How'd it go? It was great. I had a great time.
It was so fun. You do this all the time.
So guys, one thing that I want to make sure that you are maybe not comfortable with right now, but that you become comfortable with, is that the K that is given to you in the problem, you can no longer just rely on, well, that's the one she gave us, so that must be the one that we use. It might be, but sometimes it's not. And I'm not going to tell you, oh, wait, watch out, guys. This is a problem you need the Ka for, but I didn't give it to you. No. You have to be able to figure it out. What kind of K do I need, and is that what's given to me? Yes, no. Okay? Does our answer make sense?
Yes.
It does. We predicted that it would have been in the acidic range, and it is. All right. Ladies and gentlemen, let's review what we've done so far. You come across a salt, cation, anion. What's the pH? If it's strong. Correct? What if you have that? Go back and look at examples if you need to. That's basic. Okay. If you have that, acidic, okay. Exactly. Depends. Okay. Weak is not necessarily, it could be, it's not necessarily neutral. You need more information to predict that. Now, as I said before, guys, the only time you'll be asked to actually calculate something is if it's strong, weak, or weak, strong. You're not going to be calculating anything here. Okay? So how do you handle that situation? Well, let me give you an example. How about you have that salt, copper 1 nitrite. Okay? And I say to you, or I ask you, is this acidic, neutral, or basic? Let's go through that thought process. Repetition is good. Your cation forms a base, and it's a metal, so this should be a little easier than our previous example. What base? Well, what base by name? Like what compound? Copper 1 hydroxide. Okay. Strong or weak? Right. Well, wait a minute. I thought all hydroxides were strong. I'm trying to trick you. Which ones are the strong ones? Let's go through it again. Group 1 and Cabasser. Okay, so I'm going to put a little W above that copper. Anions form possible acids. What acid? Be careful. What acid is that? Nitrous acid. Not nitric. Is nitrous one of our strong acids? No, it isn't. What's the formula for nitric acid? HNO3. Good. Okay. Now, can you predict if this is acidic, neutral, or basic by just looking at it? No. You need some extra information, and that information is some Ka and Kb values. To be specific, I need the Kb value for this base, and I need the Ka value for that acid. And then you compare them, and it's logical. If Ka is bigger than Kb, it'll be acidic. If B is bigger than A, Kb is bigger than Ka, it'll be basic. If they're equal, it's neutral. Some of the problems in your problem set will reference this appendix in the back of the book. And guys, what's there? On this page, you have a big chart of Ka values. What you have in this smaller chart here are some Kb values. The chart that's down here we will deal with in our next chapter. Those are called KSPs, but we'll get to that next chapter. But have this out, okay? Here's what I'm going to ask you to do. Here are a bunch of salts. I'm not asking you to calculate anything. All I'm asking is for you to predict, are these salts acidic, neutral, or basic? Which salts are the only ones you're going to need to look down at these values? If it's weak, weak. If it's anything other than that, you don't need to look here. Right? In some of these, it might be a little bit tricky to figure out where to split the salt, but I think you can figure it out. Try these. Guys, if for some of them, if you're having issues with where do I draw that line, where do I separate cation and anion, like, for example, look at this one right here. If you're not sure where to split it, would you know where to split it if I gave you the name of this compound in words? Are you ready? Here's the name of this compound. Methylammonium, that's one word. Methylammonium fluoride. Do you know where to split it now? Methylammonium, one thing, fluoride. You're going to put the line basically right between the two words. Okay? So sometimes they'll give you a clue of where to split it by telling you the name. That helps a little bit. All right, check your answers, guys. I'm sorry it's so scattered. I am going to say something a little more in depth about this salt, but are any of the other ones confusing you? Now, let me say something a little bit more in depth about this salt right here. Okay, the sodium side in your mind you think, okay, sodium would turn into sodium hydroxide, you put an S for strong, fine. The anion is a little tricky though. All right? What acid are you thinking about that this becomes? See, the mixed answer here is what we're getting into. Some of you might have thought about sulfuric H2SO4, which is a strong acid, which is why I put S, SS, neutral, okay, fine. Technically speaking, SO4, if SO4 were to react, it would not actually form immediately H2SO4. Do you guys remember from last class when we talked about polyprotic acids, that each hydrogen comes off one at a time? Well, guess what? They're put back on one at a time as well. So some of you in this room may have thought that and said to yourself, well, that's not one of my strong acids, so I'm going to put a W over this side and say that this is a basic salt. You may have thought that, and that's not bad thinking, guys, because in all honesty, as of about 45 minutes ago, I said that this was a basic salt because I was thinking this, but then I went and I looked it up, and what actually is the case. Would I expect you to know this? No, I would not. This is a weak acid, right? It's not one of our 6 strong. Do you agree? The thing is, though, according to what I was reading, this, yes, it's a weak acid, but it's strong enough. I don't know what that means, by the way. Like, strong enough, I don't know what that means. That actually this reaction does not happen to a significant extent. And if neither ion reacts, then you have a neutral situation. Would I expect you to know that? I would not, okay? I don't know if the AP exam would, I doubt it, but maybe they would, okay? So, it is neutral, let's leave it at that, okay? So guys, this is something that you could definitely see on multiple choice because you don't need a calculator for it. Let's finish this chapter up. And the end of this chapter, guys, is all about answering the question, why are some acids strong and some acids weak? Okay? Same with bases. Like, why? What is the real reason between what makes an acid strong or weak? The reason comes from how these acids and bases are put together. And guys, the further you go on in chemistry to higher and higher levels, those of you that choose to do that, the more and more you're going to realize that the why behind every question in chemistry, really, and biology too, comes down to how are these atoms and molecules put together. It's all about structure. Okay? So there's really 2 factors that decide how acidic something is. For the 1000th time, what does it mean if an acid is strong? Complete dissociation. Okay. If something completely dissociates and breaks apart, go with your gut instinct. What do you think? Do you think that that means that these 2 particles are held together very tightly or loosely? You're right. Strong acids, complete dissociation, the bond between hydrogen and that other element is not that strong. Easily pulled apart. So bond strength is part of this factor, is one of the 2 factors. This word low, you can think of it as, you can replace that word if you don't like the word low, bond strength. weak bond strength. A bond that is easily pulled apart between hydrogen and this other element means a strong acid. Guys, remember, the word strong just means an acid that is supplying a large amount of H plus ions to the solution. Okay? If I actually gave you some numbers, you would see that, for example, the bond between HCl, a strong acid, is lower than the bond energy between HF, which is a weak bond. Okay? HF would have a high bond strength because that's a weak acid. Okay? So bond strength, there's another factor, which is bond polarity. Now we got to go back and review a bit here. Because my class this morning, they were a little rusty on this topic. If you say that a bond, not a whole molecule, just a single bond, is very, very polar, do you remember what that means? Okay, it means that one side of the bond is more positive, the other side is more negative, because there's uneven sharing of that pair of electrons. Do you remember that? You know, if I've got, let's use HF as an example. Here's hydrogen, here's fluorine. Fluorine is a very electronegative element. Fluorine is going to hog that shared pair of electrons a great deal. This is a very polar bond. A very polar bond means a very strongish connection. If these two particles are tightly bound to one another, are they going to dissociate much? No. So a very polar bond, strong connection means a weak acid because it's not going to dissociate. Okay? And you can use electronegativity values to remember that. But keep in mind, guys, we learned this, I don't know, multiple chapters ago. Your upper right-hand corner, where fluorine is, that's your most electronegative elements. Right? Just to make sure you remember this, what is the trend in electronegativity as you move down a column? Yeah, it's decreasing. They're becoming less and less and less electronegative. So, here's where I want you to focus. Just focus this column right here. Just the halogens column right there. Fluorine is the most electronegative element on the periodic table. The bond between H and F is going to be very polar. Very polar bond means a relatively tight connection, a strong bond, strongish. If that bond is strong, these two things are not going to separate very readily, which means we're talking about a weak acid. You just told me, correctly by the way, that as you move down a column, electronegativity decreases. Tell me this, what's happening to the bond polarity as I move down? Like HF, HCl, HBr, HI, are these bonds becoming more and more polar or less and less polar? Less and less, which means the connection between them is getting looser and looser and looser. They don't have HI on this chart, but if they did, HI, I would even write the word strongest acid of that group. Weakest connection, easily pulled apart. That's an acid that's providing a great deal of H plus ions to the solution. Okay? I want you to focus on that up-down direction. All right? can look here as well. These two acids, they're both weak, but look at their Ka values. This is getting stronger, right, as you move down. Last slide, ladies and gentlemen. What's an oxyacid? An acid with oxygen in it. Okay. We're going to use these four as an example. And I'm just going to write out their formulas. And I'm a little bit curious here to see how much you remember about naming acids. Yikes. Okay, we've just talked about this one today. I hope you remember this one. Perchloric, okay? When you're naming acids, guys, remember the rule is you have to remember the name of the polyatomic ion. Do you remember that 8 goes to ic, ite goes to us? Remember that rule? What's the name of this polyatomic ion? Chlorate. So what acid is this? Chloric acid. What's this polyatomic? Chlorite. So this acid is chlorous. Now this is one no one ever remembers. What's OCl or ClO with a -1 charge? Remember that polyatomic ion? No one ever remembers this one. It's called hypochlorite. So what's the name of the acid? Hypochlorous. Okay. Now, which one of these is one of our strong acids? Bottom one? Okay. And I'm just going to tell you, because you may or may not know this, not only is that weak, but can somebody give me some conjecture here? As I move down here, why are the acids getting progressively stronger? Why do you think? Every time I move down, I'm gaining another oxygen. Additional oxygens must make an acid stronger, and I want you to understand why that is. Okay? And this is only for oxyacids, okay? Because we're talking about oxygen. Oxygen is a very electronegative element. What does that mean, first of all? It does what? It pulls electrons towards itself. First and foremost, guys, I want to make sure that you are clear. Just because an acid formula is written like this doesn't mean that the hydrogen and the chlorine are bonded together. They're not. It's important that you know that in oxyacids, hydrogen is joined to the oxygen. Okay? It's important that you know that. Oxygen is very electronegative. The more oxygens there are, look at these red arrows. It means we're not talking about just one bond now. We're talking about an entire molecule pulling the electrons all to this left side. Here's the result. It is leaving that bond right there very weakened. Pulling all of these electrons over to one side is causing that bond to become very weak. Now think about it, guys. If that hydrogen can very easily be torn off, what kind of an acid must this be? Got it. As your oxygen count gets less and less, that bond is getting stronger and stronger, and if that bond is very strong, it's not going to detach easily. That's going to make it a weak acid. Okay. So you will have free response questions that will do this. They'll ask you to compare Like, I'm just gonna make this up. I don't even know if that's an acid that even exists. Probably not. I'm just making this up. Which acid would be stronger? HBrO3? Why? It has one more oxygen? Well, so what? What's so special about oxygen? It's very electronegative. Pulling electrons to one side causes that O to H bond to be very weak or weaker. Are you ready? What if I do this? What if I asked you to compare these two acids with the same number of oxygens? Which one do you think is the stronger acid? Which element, Br or iodine? Bromine or iodine? Which one is more electronegative? Bromine. The more electronegative, the bigger that red arrow is going to be. So this is your stronger acid. It's all to do with electronegativity. Okay. Ladies and gentlemen, that is the end of the chapter. Everything I just said is right here. Congratulations, you made it.